So this one is going to teach you about factoring to solve quadratic equations, and we're specifically going to use the process of completing the square. First off, the standard that we're looking at here uses the processes of factoring and completing the square in a quadratic function to show zeros, extreme values, symmetry of the graph, and interpret those in context. So you'll remember again that your quadratics, and again this is a review, so remember you don't have to have it in your notes unless you don't remember it. So our quadratic equations fit this format: ax squared plus bx plus c equals 0 usually. So the a is the coefficient of x squared, b is the coefficient of x, and then c is the additional number that's there. This becomes very important because in this equation, in the vertex equation from the last unit, and then also in the quadratic equation that we'll be using in the next setup, you need to know and be able to identify the a, b, c in a quadratic equation. So when you think about this, you're used to solving equations by factoring. So just a normal way that you've done already in the past. You can go ahead and take this piece, and it's kind of the inverse foiling is what we like to call it sometimes. And you go through and you decide what it is that will multiply to 16 and add to 8. So usually, you'll make a couple guesses like, 4 and 4, could be 8 and 1, could be, 8 and 2. How about 16 and 1? And then you'd go through each of these and see which of them add to 8. So we can see 4 and 4 add to 8. 8 and 2 add to 10, 16 and 1 adds to 17. So in the end, you'll decide that the best option for this equation, the solution, would be x plus 4 times x plus 4. So if you look at that, that's essentially a square, x plus 4 squared. Remember, that can be rewritten this way. I wonder if you guys see all the kids that are running behind my window. So this can also be written as x plus 4 squared. That's just a quick review of the basic properties of factoring. On the next setup, you'll notice that sometimes we come across equations that when we get ready to factor them, they don't go so easily. So if you notice this, multiplying to 5, I only have two numbers, 1 and 5. And neither of those add to 4. So solving this using factoring by the methods that I know already, it's just not possible. I don't have two even whole numbers that will multiply to 5 and add to 4. So that is where the process of completing the square comes in. And this starts kind of the beginning of the most important part, and it's short, you'd be surprised. So when you're completing the square, the trick is that what you're going to do is to add a perfect square to both sides of the equation and then create a beautifully factorable square. So if you notice in this example, I'm going to give you two formulas. Again, we see this ax squared plus bx plus c. That's our equation. And notice we want it in the form now where c is on the right side of the equation by itself. Then after that, we're going to use the square, and this you'll do over and over and over again. So it's a very important piece right here. It's even important enough that I'm going to highlight it with my highlighter. Okay. So when we do that, what we're going to do is we're going to take the center term, the b, divide it in half, and then square that number. So if this b were 4, we'd cut it in half to 2, and then square it, and it would become 4 again. If it were 10, we would cut it in half, which would give us 5, and then we'd square it, which would give us 25. And we'd then add 25 to both sides of the equation. That's the process of completing the square, and you'll see why it works so well. So I'm going to flip over to the whiteboard, and then we'll go through an example or two of how to go through completing the square. So I'm going to go through the process of completing the square here. And if you notice, I have my equation x squared minus 14x plus 16 written out on the paper here. And when I start looking at it, I want to be able to factor it, but when I'm looking for things that multiply to 16, I can't find any that'll add to negative 14. So if you notice, I could try 8 and 2, which will not add to 14. I could try 16 and 1, and I could also try 4 and 4, and none of those pairs add to 14 or negative 14. So in this case, this is a prime example for using that process of completing the square. So the first step in completing the square is to move the C section of your equation to the other side of the equation. So I need to move 16 to the other side, so I'll subtract 16 on both sides, and I'll be left with a new equation that's x squared minus 14x equals negative 16. Now that's a beautiful thing because I have my x squared and x by themselves on this side. Now I can use that perfect square formula that I have over here, b in half and then squared. So I'll take my b term, which is 14, divided in half, which is 7, and then square it and get 49. So 49 is the number that I want to add to both sides. Remember, I took 14, divided it in half, and then squared it. So now I'm going to go back to my equation, and I'm going to add 49 to both sides. So plus 49 on this side, plus 49 on that side, and I'm left with a brand new equation that says x squared minus 14x plus 49 equals negative 16 plus 49. So when I take 16 and I add 49, I don't want you guys to make any mistakes on these, so it's always a good idea to grab your graphing calculator and make sure that you know exactly what the answer is. And so my answer here should be 33. Okay, now that we've created a perfect square here in the front, we can go ahead and factor it and solve the equation. So I'm going to go ahead and put out my fraction bars, my factoring bars, and I'm going to ask myself, what two numbers can multiply to positive 49 and add to negative 14? Well, my options for 49 are limited to 1 and 49 and 7 and 7. Obviously, 7 and 7 would add to 14. So I'm going to go with x minus 7, x minus 7. That should work out exactly like what I want, because the way that I designed it to be added by adding the 49 to both sides was to create a perfect square. Now the nice part about that is once we've done that, I can actually solve this piece. When I have a perfect square on one side, and I can go ahead and get rid of that square by taking the square root of both sides. So I'm now the square and the square root cancel each other out, and I'm left with x minus 7 equals the square root of 33. Now I'm going to go ahead and move this along a little bit. I'm going to slide the page up, and then we're going to go in and solve for the exact number here. Now notice when I have 33 here, I want to take the square root of it, and then I'm going to add to both sides my 7. So when I take the square root of 33, I'm going to go ahead and put that into my calculator. And I'm going to get 5.74, which is my square root. However, don't make the mistake of forgetting that that square root could be either positive or negative. Since we took the square root, we have two values now. We need to split this into two potential answers. So I've got an x minus 7 equals positive 5.74, and x minus 7 equals negative 5.74. So when I do this, I'm going to go ahead and add now 7 to both sides, and I should end up on this left side with x equals 12.74, and on the other side I'm going to go ahead and add 7 again, and I should end up with x equals a positive 1.26. So in this place then, when we think about that graph that we were working on, the x-axis, the solutions, the place where the parabola is going to cross the x-axis is at 12.74 and 1.26. I don't think those are numbers that you could have come up with factoring in the first place. This next slide is an important one because it gives us a way to be able to find the vertex of a parabola by just rearranging the equation into a perfect square. This equation that you see right here at the top, y equals the quantity x minus h squared plus k. This will give us a parabola whose vertex is here at h and k. So if we can rearrange an equation into this format without having to go through the whole process of solving it, we can quickly find the vertex. So let me show an example of how to do that. So the first thing I did for you here is I rewrote the formula and kind of color-coded it. You can see to find the parabola that has a vertex at h and k, we rewrite it into this perfect square order where y equals x minus h squared plus k. So when I look at my parabola equation, the first thing I realize is that my c is on the right-hand side, and I need to move the c to the opposite side so I can make a perfect square. So I'm going to subtract 8 on both sides. Actually, I'll switch over to blue just to make it a little easier on you guys. So I'm left on this side now with y minus 8 equals x squared plus 6x. And since my equation is sitting out there ready to be made into a perfect square, I'm going to pick up that formula once again, b over 2 squared. And that's going to give me the term that I need to add to the side here in order to make this a perfect square. So my b is 6, so I'm going to take 6 divided by 2, that gives me 3, and square it for 9. So the number I'm looking here to add to both sides is 9. My perfect square is 9. So I'm going to add 9 to the right side. You remember the brother and sister rule. If you add it to one side, you have to add it to the other. So now when I do this and I rewrite my equation, I have a y plus 1 equals x squared plus 6x plus 9. My right-hand side of the equation is set up to be a perfect square, so I'm going to go ahead and factor it into a perfect square. It should be x plus 3 times x plus 3. 3 times 3 will give me 9. 3x plus 3x will give me 6x. So I'm going to rewrite that once time to make it perfect. You get it? It's already a perfect square. Come on, guys, I'm a little funny. So it'll be y plus 1, which just carried down from the top, equals x plus 3 squared. Now, my formula up here to find the coordinates of the vertex tells me the the y has to be by itself. So in order to do that, I'm going to subtract 1 from both sides, and I'll get y equals x plus 3 squared minus 1. Now I've gone through all of that work just to be able to turn around and say, okay, well, where then is the vertex of my parabola? So remember the formula here says it's x minus h. Right here is my h, and then it has a plus k on the end. So if you notice over there on the end is the plus k. So you should be able now to figure out that the k on the end here is -1. That's the number that's being added. And you'll notice here in the middle it says y minus h. Well, since this is written as a plus, or as a positive, we kind of need to, in our head, to rewrite it as x minus -3, because it has to be written as a minus. So that being the case, my h then becomes -3. So when I graph this parabola, I'll find that its vertex is at -3 and -1. So I thought you guys might enjoy a little bit of fact checking. This was the equation that we started with, y equals x squared plus 6x plus 8. And we decided that the vertex was at -3, -1. I thought we'd do a good job to turn around and just double check that that's actually where it is. So you can see I've added my x squared plus 6x plus 8 was my original equation. Desmos is nice enough for me. It highlights both my zeros and then also gives me the equation there of my vertex. So -3, -1 is the correct place for it. Again, this is the Desmos calculator site. It's DESMOS, and it does a great job in giving you another way of double checking your equations. Okay, that brings us now to the last slide. I thought you guys might enjoy this little completing the square joke because you've spent the whole block completing the square. So give it a go. These are definitely worth doing 2 or 3 or 4. Don't forget that formula of taking the center term, which is the b, dividing it by 2, and then squaring it to add to both sides.